In our intro to limits video, we talked about being able to find a limit using three different methods. Number one was the graphical method. We just checked that off in the last video. In this video, we're going to try to find those limits using a table. And then in the next series, we'll focus on finding those limits algebraically or analytically. So this table one might be the easiest one, which is really nice. And it doesn't matter whether it's graphical or tabular or algebraically. It's taking the same information and just organizing it and presenting it in a slightly different perspective. So again, our definition is a limit measures a function's intended height, not its actual height. And of course, as the input values get closer and closer to one specific value, what do the output values get closer and closer to? So organized in this table, we're going to talk about, what is the limit as x approaches 7, right? And so you'll see here, the inputs right here are getting closer and closer and closer to 7. While that's happening, what are these outputs getting closer and closer to? Okay. Those limit outputs are getting closer and closer to 8. So all we're going to say is that the limit as x approaches 7 from the from the left equals 8. Okay. And again, it doesn't matter what they put right here. They can put anything. It doesn't matter whether they say undefined or they put a number there, and it could be any number. My answer is going to be 8 just by looking at what I shaded in purple. What they put right here it's totally meaningless, All right. Now let's take a look at the other side. You notice these inputs are getting closer and closer and closer and closer to 7, aren't they? Okay, we're sneaking up on the 7 from the right-hand side. And while that's happening, the output values are getting closer and closer and closer to what? 8 again. So what we'll say with great notation here is the limit, LIM abbreviates the limit, x approaches 7 from the right-hand side equals 8. So what we're saying is the intended height of the function is equal to 8. Now again, check this out. Our one-sided limits, the two different one-sided limits, both equal to 8. So now we could summarize that and say the general limit as x approaches 7 of f of x equals 8. Winner, winner, chicken dinner. All right, new table. And you'll notice who's sitting in the center of our table. We got ourselves a real cute little 0 right here. And again, just put an x through this. That means nothing to us. What is the limit as x approaches 0 from the left-hand side? So as the inputs are sneaking up on 0 from the left-hand side, what are the corresponding outputs approaching? Now, this is a slightly trickier one. Now, you may be tempted to say 1.6, and you're almost right. The limit as x approaches 0 from the left-hand side of f of x is equal, now you could say 1.6 repeating, but what I would rather say is 7/3, okay? The fraction is a more preferred version when it comes to a repeating decimal, okay? In my opinion, anyway. Now, what about the other hand side? So we start here and we inch our way closer and closer and closer to 0 from the right-hand side. These corresponding outputs are getting closer and closer to 1.6 repeating, okay? And so we're just going to do something really similar. We'll say the limit as x approaches 0 from the right-hand side is equal to 7. Oh my gosh, that's not 7/3. Hold your horses. I hope you were scratching your head wondering where in the world I came up with 7/3. I believe that should be a 5/3, right? Do I have this right now? Somebody give me a thumbs up. All right, so let's say 5/3. That would be 1 2/3 or 1.6 repeating. So let's go 5/3. How about that for embarrassing myself, huh? And again, we got the same answer, so we could kind of combine that information and say the general limit as x approaches 0 of f of x is simply equal to 5/3. See how easy these tables are? Now, sometimes what they'll do with these tables, and I don't think I have one in this video, but they'll give you the input values. Like they'll give you these numbers, but then this row here will be blank. And all you do is you just use your calculator to substitute a 4.9 and a 4.99 for x, and et cetera, et cetera. And again, they'll supply you with the function or the equation for f of x. So in this particular case, all we're going to say is it looks like x is approaching 5 from the left. And while that's happening, we're getting closer and closer to, what do you guess? Yeah, it looks like a 75. And if we jump to the other side of 5 and we said, okay, let's approach 5 from the right-hand side, the corresponding values of x are getting closer to 75 again. The limit as x approaches 5 from the right is equal to 75. And we got the same number for both sides. So the general limit is going to be 75. We got a good streak of our general limits existing, don't we? Now, I threw this example in there for a couple of reasons. I wanted to prove that our tables don't have to be set up horizontally. They could be set up vertically, and that's totally okay. So what we're going to do here now is, and again, this was kind of cool. They kind of showed you who f of x is. F of x is this function right here. And you'll notice by looking at the denominator, x is not allowed to equal 4 because then you'd be dividing by 0, and that's why you see the error or the does not exist mention there. But again, it doesn't even matter. We're just going to cross that off. That doesn't affect my answer at all. All right, so what you'll notice here, as the x values get closer and closer to 4, the corresponding outputs get closer and closer. It looks like negative 16,000. So let's say the limit as x approaches 4 from the left equals negative 16,000. All right. Now, if we jump to the other side, and maybe I got to shimmy up here just a little bit. Now we're going up the table here, and the inputs are, as I go up the table, we're getting closer and closer and closer and closer to 4. The corresponding outputs are getting closer and closer and closer to 16,000, positive 16,000. So we'll say the limit as x approaches 4 from the right is positive 16,000. Now again, these two limits are not the same, so we would just summarize this by saying the limit as x approaches 4 of f of x does not exist because we got two different answers. All right, one last one. Here's an example where we may not know exactly what the limit should equal just by looking at the table, okay? Now, we're going to do the limit as x approaches 5, and we're going to do it from the left and we're going to do it from the right. So you're going to use this information right here to do the limit as x approaches 5 from the left. In this case, it's g of x. Notice that name right here. And then you're going to use this information to do the limit as x approaches 5 from the right of g of x. What you don't want to look at, don't even look at this number. That's the most useless, irrelevant number within the context of this question that you'll ever see. All right, so let's just focus on the left-hand side. As I approach 5, I'm getting closer and closer and closer and closer to 5 from the left. Now, the corresponding outputs are getting closer and closer to, Now, there's a degree of freedom here. Like if you said 3.7, I'm okay. Like I think based on the information we have at our disposal, saying 3.7 is good. If you said 3.8, I'm okay. If you said 3.9, I'm okay. If you said 3.69, I'm okay. So this would really be just like a ballpark answer. We don't have necessarily maybe enough information to get really specific, because you'll notice the jump. Look at this jump from 3.66. It only jumped to 3.68. So I wouldn't say like if I went to 4.9999, I don't know as it's going to jump all the way to 4. It looks like, because usually the jumps get smaller and smaller and smaller as you inch your way closer to the 5. So I might even be tempted to just say, 3.69. And in that type of question, it may be a multiple choice question, and they'll just ask you which answer seems the most reasonable. And certainly in this case, like 3.69 is way more reasonable than saying 8, or -2, or doesn't exist, because it certainly looks like it does exist. Now, on the other side, as we approach 5 from the right, we're going to inch our way So we're starting here. We're going closer and closer and closer and closer to 5. Meanwhile, the outputs are getting closer and closer and closer again. Look at that last jump. It went from 3.7 and it only jumped down to 3.68. Again, it was a very small jump. And usually the jumps get smaller as you go. So I might be tempted to say 3. Now, again, it looks like they're decreasing. So it's dropping. So I may be tempted to say 3.67. Based on the information I have at my disposal. But again, it's a ballpark answer. If you said 3.65, I'm okay. If you said 3.5, I'm okay. 3.6, I'm okay. If you said -3, now we got problems, right? But it does appear that the two answers are slightly different. So we would say that the general limit as x approaches 5 doesn't exist.